This is a bit of an experiment, so it may not work, but I'm going to try and measure the whole of the universe in 15 minutes. So I've got a timer here, so we're going to start it. But I'm going to share the burden, so you're going to help me to measure the world in 15 minutes, okay? So it's a little bit of a challenge out to you, whether we can get through the whole of the universe and measure it. Now, the Institut de Poids et Mesure in Paris has identified 7 units of measurement with which you can use these 7 to measure anything you want to in the universe. So the challenge for you is to identify what 7 units can we use to measure the whole of the universe. So you just got to shout them out, and it will dictate how my talk goes. Okay. So any ideas? What sort of things do you need to measure? Units of measurement. A second, okay, time. So that's actually the first one. So the second was the first unit of measurement that we really came up with. Measuring time actually is a very mathematical property because you've got to spot patterns in order to be able to measure time, because it's about things repeating themselves. And in a way, it's the oldest sort of measurement we made, because if you go to the Lascaux caves, it's believed 17,000 years ago, this painting on the wall is believed to be a calendar. And they think that these dots on the wall were representing weeks, quarters of the moon. And it was a sort of repeating pattern. They could see 13 of these, then another 13, then another 13. And they think this was basically a manual in order to be able to tell people when to hunt, because these aurochs were pregnant at a particular stage, 13 weeks past the equinox. And so this early calendar was thought to be the first measurement of time. But of course, we're looking for things which are periodic to measure time. So the day, the fact that the sun repeats itself. And so this is the reason that we came up with a second. Actually, the second comes from Babylonian times. We like to work base 60 in Babylonian times. 60 is a very divisible number. So they divided the day up into units of 12s, 24s, 60s. And so the second comes from the Babylonian counting system. We work base 10. The Babylonians work base 60. Okay, we're meant to get onto another unit of measurement. So that's the solar day. But actually now it's defined not by the sun at all. It's defined by something totally universal, which are energy levels in atoms of cesium. So when you excite an electron, it shoots up and it comes down again. There's a very specific frequency that comes out, and that we use that to measure time. So the second now is defined as the duration of 9 billion and a bit more periods of the radiation corresponding to the transition between the 2 hyperfine levels of the ground state of cesium-133 atom. Okay, next unit of measurement. Mass. Okay, excellent. So let's get out to our universe. Oh yeah, there's a clock. That's an atomic clock, believe it or not. So that measures time. So mass. Interesting. That's one down here. Okay, so mass. Yes, mass is a very interesting one. We measure in the kilo. This was a unit of measurement that was defined by the French. In fact, this is one of the unique measurements, because this is still a 19th century definition. We haven't upgraded this one. So here it is, Le Grand K, which is kept in a safe in Paris. It's probably the most valuable piece of metal on the Earth because it defines the kilo. Unfortunately, it seems to be losing atoms. Now, that means this defines the kilo. So it's not changing weight or mass. It's actually staying the same. It just means that we're all getting heavier. Which is a real blow. So actually we're trying to redefine the kilo as something else. So there are 2 rival definitions. Oh yeah, it's so secure this. There are 3 people with keys from different continents who arrive to open it and check it's still there every year. And we got to see this every October. But there are 2 rival definitions at the moment for the kilo. One is counting the number of atoms in a silicon ball. So this ball is an extraordinary smooth object. If this was the size of the Earth, the differences between the valleys and the hills would be just 2 meters. And so they try to count the atoms inside this kilo, and that will define the kilo. That certain number of atoms of silicon will define what the kilo is. But there's a rival one, which is actually something called the watt balance, which they're trying to use sort of electricity to be able to measure how much magnetic field you need to actually keep a weight balance on there, and that might define the kilo. Okay, next unit of measurement. On to the third one. So another one, please. Distance, feet. Yeah, feet are rubbish, actually. So we actually use the meter. So where's the meter? It's this one here. Actually, feet is quite interesting because, of course, we used to use our bodies to measure things. And in fact, if you go, one of the reasons the Egyptians and the Babylonians were such great civilizations, they were one of the first to measure distances, and they would use bits of their body in order to measure the distances. So this is what's called a cubit. So the cubit was the distance from the elbow to the tip of the pharaoh's finger, and that would be used to measure things in Egypt. And so the feet, of course, come from the same thing. We use our bodies, or a yard. In fact, a yard was defined as the distance between the nose. Yeah, this is quite difficult. Between the nose of the king and his outstretched thumb. His outstretched thumb. And so this would vary according to which king was in power. And actually, Queen Elizabeth added a little bit extra because she didn't want to be beaten by the others. So the French said, we've got to define it on something universal. So they defined it using something which belongs to everyone, the earth. So the meter, how do you define the meter? The meter was in fact defined as 1/10,000,000th of the distance from the North Pole to the equator. No one knew what that distance was. So two guys were sent off during the French Revolution to measure the distance. One started in Dunkirk, the other started in Barcelona, and they worked towards each other to try and measure the distance. And they did it all using triangles and trigonometry. They did one measurement of distance, and the rest was just triangles all the way to Barcelona. And they used this amazing thing which measures angles between these things. Oh gosh, we got it. But actually, the Earth is not a terribly good thing because these two people took 7 years to measure it. So actually we define it in a different way now. The speed of light in a vacuum is a constant. So it's actually defined now. The meter is the length of the path traveled by light in a vacuum during a time interval of 1 over 299 million and a bit more of a second. So that's the meter. Okay, so we've done three. We've done 3 now. Excellent. Any more? What was that? Speed. Speed's made out of meters and seconds. Volume. Gosh, what the hell is volume made out of? That's pressure, probably. So that's probably a kilo and meters and seconds. You can do volume in. Heat, excellent, great. That one's this one here. So heat is definitely one of the units of measurement. So it's temperature. And temperature, the unit of measurement that we use for the temperature is something called the Kelvin. So it's actually Galileo who realized that, in fact, to measure temperature, you can change it into measuring lengths. So what do? We use a thermometer. It's the change in size of something. So we just measure a length, and that tells us the temperature. And there were several rival scales. I've always been intrigued. Fahrenheit. Why on earth does it start at 32 degrees Fahrenheit for freezing water? Do you know why? I'm going to tell you, because, in fact, what Fahrenheit did, Daniel Fahrenheit, the coldest he could get in his lab was putting a combination of ice and salt together, and he said that was 0. And so he could get that colder than ice. So ice turned out to 32. And again, this obsession with 180 and 360 meant that he used that scale rather than the sort of Celsius. Celsius used the sort of scale from 0 to 100, very French sort of style of things. But they were both outdone, actually. So we now use what's called the Kelvin. So Lord Kelvin realized that, in fact, what is temperature? It's the movement of molecules. So if they don't move at all, that's the coldest anything can be in the universe. So that's taken as the bottom of the Kelvin temperature scale. And there's another really interesting point. There's a weird moment when water can both be a gas, a liquid, and a solid. It sort of freezes the ice, and this point is a very specific point. It's called the triple point of water, and we use that to measure the Kelvin. So the Kelvin is actually defined in using these 2 points. Okay, so we've done 4, 3 more to go. Energy is made out of kilo and mass. If you think of it, E equals mc squared. Kilo times speed squared. So that one, I don't know. Which one? Weight? Waves. Radiation, that's kind of interesting. So that's probably measured. You can measure that with a frequency. So I'm not sure that one. Light. Okay, good. That's quite an intriguing one. So light. In fact, that's a really difficult one. You've done quite one of the hard ones, which is luminosity. So the candela is a measurement of how bright something is. So we can measure the brightness of these lights using this measurement called the candela. It was actually it started right back when we had gas lamps, and we wanted the gas lamps to be a certain intensity. So it's defined as a candle power, which is the light produced by a pure spermacetum candle weighing 1/6 of a pound and burning at a rate of 120 grains per hour. Spermaceti candles were made out of the bit of the sperm whale that they thought was the sperm of the whale, but wasn't the sperm of the whale. So this bit up here, and so that was defined as the unit of measurement of intensity of light. But now we've upgraded this. But this is a kind of really weird measurement because, in some sense, it depends on our human perception of light, and our human perception of light kind of varies according to what color you're looking at. If you look at these, actually, red has completely something's wrong with your projector because that one's meant to be red. So, but interestingly, out of these three, the one in the middle is not the brightest. We tend to see green as brightest because, probably for evolutionary reasons, we saw a lot of green. We're very sensitive to green. The cones in our eyes, the blue cone also picks up green as well, which probably Bo is going to confirm, hopefully. Okay, so the candela now is defined as this extraordinarily complicated thing here. So, okay, so you've got two more to go. You're doing incredibly well. Electricity. Did somebody say electricity? Or did I just make that up? Good. Yes, electricity. Absolutely. I kind of said electricity because that's what the watt balance. Oh, no, I've told you the... Oh, let me tell you about this one. So this is the extra one, okay, which is quite a difficult one, but it's actually my favorite. This is the mole. Now, the mole, how many did A-level chemistry? Any... Now, didn't you hate, doesn't that give you a kind of like weird, horrible feeling? Oh, God, the mole. Because the mole is what on earth is the mole? The mole actually counts number of things in something. So the mole is defined as the number of atoms in 12 grams of carbon-12. So it's kind of, what unit of measurement, what is this measuring? It's just measuring number. It's making number a unit of measurement. So how many atoms are there? Well, there are a hell of a lot. There are 6 times 10 to the 23. So that's 6 with 23 zeros after it. But actually, it's a very useful unit of measurement because if you're doing chemistry, if you're saying that you're trying to make water out of hydrogen and oxygen, you can say that 2 moles of hydrogen atoms and 1 mole of oxygen atoms actually makes 1 mole of water. If you try to do it with weight, which is perfectly possible, it'd be a very messy calculation. But you can do a mole of anything. I can do a mole of the audience. We haven't quite got a mole of the audience. That's a bit disappointing. But I was thinking, you could, actually, I was on the midweek with Ruby Wax, and she was going, I thought you were talking about the animal, she said. So I thought, let's consider a mole's worth of moles. What would that look like? What would a mole's worth of moles look like? Well, actually, if you cover the whole Earth with a mole's worth of moles, it would pretty much go right up to the top of Everest. You would sort of cover the whole of the surface of the Earth. With 6 times 10 to the 23 moles would cover that amount of the Earth. If you put them all together, they would sort of compress because gravity pulls them. It'd go a bit squishy. It'd be pretty nasty. But actually, it'd be about the size of the moon. So a mole's worth of moles is about the size of the moon. And in fact, you could even cover it in mole sauce. So you've got mole's worth of mole in mole sauce. So that's the unit of measurement. And good. So I gave you that one for free because I pressed the wrong thing. So electricity was the last one. So you're doing incredibly well. So electricity, actually, there were 3 different rival things that they could have measured because electricity, if you remember from electricity, you have something called the voltage, you have the resistance, which is measured in ohms, and the ampere, which is a measure of current. And so these were 3 guys. So Volta in Italy measured volts. Ampere, let's go back. Ampere measured current, and ampere was from France. Ohm was from Germany, and because it was the French who were deciding all the units of measurement, of course it was the ampere that was chosen as the one that would be the basic unit of electricity. So everything else can be measured, ohms and voltage can be measured in terms of the ampere. And so when you run a current through things, it makes a magnetic field, and that attracts towards each other. So the ampere is defined as the constant current that will produce an attractive force of 2 times 10 to the minus 7 newtons per meter of length between 2 straight parallel conductors of infinite length and negligible circles cross-section placed 1 meter apart in a vacuum, which looks something like this. Now, that's absolutely fantastic. You've managed to measure the Earth in actually 14 minutes. And the amazing thing is that if you can't measure anything with this, basically it means that you don't really understand it. Thank you.